Assalamualaikum. In this session, we are going to learn about mass spectrometry. Mass spectrometry is an analytical technique that measures the mass to charge ratio of a charged particle. It is used for determining the mass of a molecule, the elemental composition of a sample, and it helps us to elucidate the chemical structure. The mass principle consists of ionizing chemical compounds to generate charged molecule or molecule fragments and measure their mass to charge ratio. What information that can be determined from the mass spectrum? We can know about the molecular weight, the presence of certain structural units in the molecule, and the isotopic incorporation or distribution. Fact in the mass spectrometry. This mass spectrometry is not calling as spectroscopy. Why? Because it does not involve the absorption or emission of light source. That's why in mass spectrometry there are no light source. They involve the high energy of electron and breaks the molecule into the ions. And the ions or the fragments will be measured their relative abundance, and they will reveal the information about the structure of the molecules. Application of the mass spectrometry can be in the different fields such as pharmaceutical analysis, biomolecular characterization, environmental analysis, and forensic analysis or clinical. Background of the mass spectrometry. Mass spectrometry uses high energy to break a molecule into fragments. Based on the ion form, they will be separated, and the fragments provide information about the molecular weight and the structural unit. Here I show you the chemical equation, how the high energy electron bombard our neutral molecule to form the ion. This high energy of electron will bombard our neutral molecule, and one electron here will be released, and this form become a cation. This molecule become radical cation, and one electron has been released followed by the electron of the high energy. Based on this, only the radical cation will be detected, and these neutral molecules are not detected. So next example, the high energy electron not only bombard for the certain bond in the molecule, it can be everywhere in the molecule, whether in the middle or the right or the left side. So we can see here the electron bombard one electron here, and then it become cation here, radical cation form. And when the electron bombard both electron, and both electron have been released, so hydrogen have been become a radical, and the left part become a cation. And the next electron bombard in the middle of the bond, and it become half part become a radical, and the half part become a cation. Only the one that had been written down with the MZ value appear in the mass spectrum. This one are not appear. In fact, that radical are not detected for the mass spectrometry. Here, after it had been bombarded and formed the radical cation, this radical cation always appear in the mass spectrum as the molecular ion peak. And the molecular ion peak had a definition with the highest mass in the spectrum. and this is the definition for the molecular ion peak. And another stable cation always form the largest peak, the highest intensity of the peak is called a base peak. Let's see the mass spectrum. This is how the mass spectrum looks like, where the x-axis will be the mass to charge ratio and the y-axis will be the relative abundance of the ion. The molecular ion peak, where is the molecular ion peak? The last peak or the highest mass to charge ratio is called a molecular ion peak, or another terms is called as a parent ion. This parent ion tells us about the molecular weight of our molecule, and this the highest intensity of the relative abundance is called a base peak. Why the base peak is formed? Because the cation is the most stable. Other peak in the mass spectrum is called the fragmentation peak. After we know the definition of the peak, so where is the molecular weight of ethanol? So in this mass spectrum, you can see the molecular weight is the last peak or the highest peak for the MZ value, telling us about the molecular weight for the ethanol. In this case, the molecular weight for ethanol is 46. This is the base peak, means this cation is the most stable cation. Now we move to the process what happened inside the mass spectrometry. As I mentioned just now, the neutral molecules must ionize first to form the ion, and this ion will be accelerated through the tubing in the mass spectrometry, and after they pass through the magnet, they will be deflected and they will be separated based on the mass of the ion, and the ions that are too heavy will bend too little, and the ions with the right mass can enter the detector, and the detector will detect the cation form with different mass and have different peak and fragmentation peak. So this is the 4 stages for the ion process in the mass spectrometry. The first stage is ionization, the second stage is acceleration, the third stage is deflection, and the fourth stage is detection. Only cation are detected in the mass spectrometry. Radical are invisible. Invisible means not appear in the mass spectrum. So the amount deflect observed depends on the mass to charge ratio. That's why the intensity of different peak will be different because of different relative abundance of the cations form. Mostly cations form in the form of positive 1 charge. The relative mass of mass spectrum, as I mentioned just now, the x-axis will be the mass to charge ratio, the y-axis will be the relative abundance. The most stable peak is called a base peak, and the last peak or the maximum mass to charge ratio is called a molecular ion peak. Others than the molecular ion peak, fragmentation peak, what else information that we can get from the mass spectrum is the presence of isotope. In the mass spectrum, it can be differentiated between different isotopes based on the M+1 and M+2. When the presence of this characteristic, it shows us that they are naturally the elements are in mixture of isotope. M+1, what it means? A peak that is 1 unit mass higher than M+. M+2, a peak that 2 mass unit higher than M+. M+1 peak first. As this spectrum, we can see the M+, there is molecular weight of this propane molecule is 44. There's another small peak with the M+1, which is 45. What it means for this peak? This is only 1% of the molecular weight peak. These peaks contribute to the presence of isotope C13 in the organic compound. As we know, in the organic compound, 99% of the organic compounds presents the C12 and only 1% is C13. This peak in the molecule in the mass spectrum shows us the presence of the isotope C13. Next, M plus 2. When this peak presents in our mass spectrum, it shows us that the presence of major isotope, which is halogen isotope. For the M plus 2 peak with the characteristic of 3 to 1 ratio, if they have this characteristic, so it means it shows us that chlorine presents in our molecule. Why it have 3 to 1 ratio? Because chlorine 35 is in natural abundance is appear as 100% compared to the chlorine 37%, chlorine 37 with 30% only. That's why the ratio is 3 to 1 ratio when it present in the mass spectrum. And another characteristic is M plus 2. There are two characteristics that we can recognize the presence of chlorine atom. Next, if the peak with the 1 to 1 ratio with the M plus 2, we know that bromine atom have been present. Why? Because the bromine in natural, the bromine 79 is 50% and bromine 81 only 49%. Ratio is quite similar. That's why we can see the peak of 1 to 1 ratio. If these two characteristics, M plus 2 and 1 to 1 ratio, so it means and it shows us that bromine atom have been present. So we can see the example for the mass spectrum of chloropropane here. So this is the M plus with the MZ value 78, and this is the M plus 2 with the MZ value 80. So M plus 2 80, M plus is 78, and the ratio with 3 to 1 ratio. So this clearly shows us that chlorine is present in this molecule. Next example, same. M plus and M plus 2 with the 3 to 1 ratio. So this shows the chlorine presence in this molecule. Next example also same with the ratio 3 to 1, M plus and M plus 2. So this shows us the chlorine presence in this molecule. And next example for bromine molecule with the charge ratio with the ratio 1 to 1. So the MZ value will be 1 to 2, and with the M plus 2 1 to 4. If these two characteristics appear in the mass spectrum, so we know the bromine atom have been present. After we know why we have a different ratio of the peak, because in natural abundance they are not in the same ratio. That's why it appears some is become a 99 ratio to 1, 3 to 1, 1 to 1 because of the natural abundance. And we can see carbon 12 is 100%, carbon 13 is only 1%. Chlorine 35 is 100%, chlorine 37 is 32%. That's why this one is 3, this one is 1. So bromine is 100%, bromine 79 is 100%, and bromine 81 only 80%, 98%, so it become 1 to 1 ratio. So another peak rather than molecular ion peak, base peak, fragmentation peak, also known as metastable peak. Metastable peak, why it formed? Because metastable ions fragment slowly after passing through the ion source and they reach to detector. So the characteristic of metastable peak, they do not necessary to occur at integral MZ value. They are much broader than normal peak. They are relatively low abundance. So for metastable peak, although they appear, we are not tend to elucidate their structure. Easily recognized. Other than isotopic information, we also can recognize some strength in the mass spectrum. If we expect our compound to have nitrogen, so they have a nitrogen rules, whereas when we see the odd number of molecular weight, so we can know that the odd number of nitrogen present. As we know, nitrogen atom is 15, that's why if one presence of nitrogen atom, it will contribute to the odd number of the molecular weight. If we expect to have 2 nitrogen atoms, so it will give us 30 actually, so total molecular weight become the even number. Other than nitrogen, easily recognized element in the mass spectrum is iodine. Iodine, as we see on the table before, they have no isotope, so how we can recognize the presence of iodine atom? So iodine itself will form a peak at 1 to 7 and with a large gap for the fragmentation peak. So this can easily recognize that iodine is present in our molecule. Okay, that's all for this session. Thank you.